All right, let's pull back the curtain on a super powerful math idea that, believe it or not, you use every single day, probably without even realizing it. It's called the Cartesian product, and it's basically the secret engine running behind every grid, every list, every coordinate system you can think of.
No, seriously, think about it. The cells in a spreadsheet, the coordinates you plug into a map, even yelling B5 in a game of Battleship, they're all built on the exact same mathematical DNA. So today, we're going to break it all down.
Okay, so to really get this, we're going to start with something you already know and just take it apart. We're going from the grids we see all around us, and we're going to look at their most basic building blocks, which in math are called sets.
So just picture a really small, simple theater. We've got two totally different groups of things, right? First, you have the rows. Let's call this group set A, and it's just got row A and row B in it. Then you have the seat numbers. We'll call that set B, and it has seats 1, 2, and 3. And yeah, in math, these simple little groups are just called sets. Pretty straightforward so far.
Okay, so here's the big question. How do we mathematically describe the process of making every single possible seat assignment? What's the formal name for the action of pairing every single row with every single seat number to get A1, A2, A3, B1, and so on? I mean, there's got to be a name for that, right?
And of course there is. This whole pairing process has a name. It's called the Cartesian product. You'll also hear it called the cross product a lot, and that's just because of the little X symbol it uses. So let's check out the official definition.
So the Cartesian product of our two sets, which we write as A cross B, is simply the collection of all possible ordered pairs. And an ordered pair is exactly what it sounds like. It's a pair of things, like A comma B, where the order is super important, and the rule is absolutely strict. The first thing in the pair, the A, has to come from the first set, set A. And the second thing, the B, has to come from the second set, set B. No exceptions.
And here's what that actually looks like. It's pretty systematic. We just take the first thing from our row set, which is A, and we pair it up with every single thing in the seat set. That gives us A1, A2, and A3. Then we just move on to the next item in the row set, B, and do the exact same thing. B1, B2, B3. And that's it. This complete collection of all 6 pairs, that is the Cartesian product. It's the whole universe of every possible seat in our little theater.
Now, I've been saying ordered pair over and over, and I'm doing that for a reason. That first word, ordered, is absolutely non-negotiable. In fact, it's probably the most important rule to remember about the Cartesian product. The sequence is literally everything. I mean, this is the key takeaway, for real. When we write that pair A comma B, that first spot is reserved exclusively for something from the first set, and the second spot is reserved for something from the second set. That positioning is absolute. You can't just flip them around.
And this right here shows you exactly why. A cross B gives us a pair like A1. Okay, cool. Row A, seat 1. That's a real seat. You can buy that ticket. But if we tried to do it the other way, B cross A, we'd end up with pairs like 1 comma A. What does that even mean? Seat 1 row A? That's just gibberish. That seat doesn't exist. And this proves a really crucial point in math. A cross B is not the same thing as B cross A.
Okay, great. So we know how to list out all the pairs. But, I mean, what if our theater was huge, like 50 rows and 100 seats? You're not going to sit there and write out 5,000 pairs by hand. No way. Luckily, there's a super simple, beautiful little formula to get the total number instantly.
Okay, so let's look at the size of our sets again. Our row set, set A, has 2 things in it. And our seat set, set B, has 3. So, with 2 rows and 3 seats, how many total unique seat pairings can we possibly make? Come on, I bet you've already got the answer.
Of course it's 6. The formula is just so simple and elegant. You just multiply the number of items in the first set by the number of items in the second. The fancy way to write it is n of A times n of B equals n of A cross B. But for us, it's just 2 times 3 equals 6. Yep, it's really that easy.
So, okay, now you totally get the Cartesian product. But here's the big reveal. The product itself, it's not actually the end goal. Think of it more like a launch pad. It's the foundation for something way bigger, one of the most powerful ideas in all of math, actually.
Just remember, what the Cartesian product gives you is the entire universe of all possible pairings. Every single combination that could ever exist between those two sets. For our little theater, that's all 6 of those seats. But let's be real. What if we don't care about all of them? What if we only want to focus on a specific selection of those pairs? Like, say, we only care about the aisle seats. Just seats A3 and B3. How do we talk about just that specific little group?
Well, that specific group is called a relation. It's that simple. A relation is just any smaller group or subset that you pull out of that giant Cartesian product. And the pairs you pick for your relation are usually chosen because they all follow some kind of rule, like the rule is an aisle seat. And this is the bridge that connects everything we just talked about to really big topics like functions, databases, and even network graphs.
Okay, so let's do a quick recap of the most important stuff. First, the Cartesian product is what creates all those possible ordered pairs from 2 sets. Second, it's the hidden engine behind pretty much any coordinate system. Third, and this is a big one, order is absolutely critical. A1 is not the same as 1A. Fourth, finding the total number of pairs is easy. Just multiply the sizes of the sets. And finally, and maybe most importantly, the whole product is the foundation that lets us define and find meaningful relations.
So, from now on, whenever you look at a spreadsheet or a map, or even just pick your seat on an airplane, you'll know about the elegant, simple math engine that's working just under the surface. Now that you can see this fundamental structure, I've got a question for you. What other parts of your world are built on these hidden mathematical grids? Think about it.